My dear student, I am A.K. HAZRA from Salt Lake City, Kolkata. I wholeheartedly welcome you to School of Fundamental Sciences for our confidence building program. This intensive program will help you a lot to understand the fundamental concepts of physics, chemistry, mathematics steadily. I earnestly request you to study the content of our videos very carefully. I will be happy if you understand and enjoy the useful concepts. My heartfelt wishes for your bright future. Thank you. My dear student, let us start balancing of chemical equations. A review of concept number 1, idea of a redox reaction. We have large number of chemical reaction in which the reduction and oxidation takes place simultaneously, and this reaction is known as redox reaction. Now, reduction is a process in which the reactant absorbs electrons, and oxidation is a process in which the reactant releases electron in the reaction. Now, for example, if we have H2SO4 plus 2H plus 2E minus, since electrons are absorbed by the reactant, it is a reduction process. And Br minus to Br2 is oxidation process because electrons are released from the reaction. If we add the two reactions, we will have this reaction H2SO4 plus 2H plus 2Br minus, we will have SO2, Br2 plus H2O, electrons are cancelled out. And this is a redox reaction because here the oxidation and the reduction takes place simultaneously. And to understand the balancing of the redox reaction, we need the concept of oxidation state, that is oxidation number. Now we will discuss the concept of oxidation state or oxidation number. Now, review number 011, the concept of oxidation state or oxidation number of an element connected by covalent bond or covalent bonds. Now, oxidation number or oxidation state of an atom is defined as the charge the atom in the species would have if all the covalent bonds connecting it with the other atom or atoms are considered to be completely ionic by assumed heterolytic fission. For example, heterolysis of MX covalent bond where M is less electronegative and X is more electronegative. It is a covalent bond. The bond is formed, yes, due to one electron coming from M and the second electron coming from X. Heterolysis means complete transfer from less electrovalent M to the more electrovalent X. So what will happen? In this dissociation, in this cleavage, M will lose one electron, so M will have the charge 1 plus and X will have the charge 1 minus. Yes. Now, as per the definition, the charge plus 1 for M, so the oxidation number of M is equal to plus 1, and charge for X is 1 minus, so the oxidation number of X is minus 1. Thus we have for one covalent bond, oxidation state of M is equal to plus 1 and the oxidation state of X equals to minus 1. Similarly, if we consider the heterolysis of MX connected by double bond, what will happen? For the heterolytic fission, this bond, these two electrons will completely transfer to X. Similarly, the two electrons for this bond will completely transfer to X. So M loses 2 electrons, so it will have the charge 2 plus. X will gain 2 electrons extra, so 2 minus. So the oxidation number of M is plus 2 and the oxidation number of X is minus 2. Similarly, if we have the 3 covalent bonds, we will have oxidation number of M is plus 3 and the oxidation number of X will be minus 3. Now sample example. Number 1. Compute the oxidation number of hydrogen and oxygen in water. No, so first we will have the what? First we will write the Lewis structure of water and then assume heterolytic fission for the OH bond, OH covalent bonds in water. So let us see, it is the Lewis structure of water. Now, since oxygen is more electronegative than hydrogen, for heterolytic fission of this OH bond, the two electrons will go to the oxygen side. Similarly, these 2 electrons will go to the oxygen side from this hydrogen on the right side. So ultimately oxygen will have 2 electron extra, one from left, other from right, so 2 minus charge. Hydrogen loses 1, so 1 plus, this hydrogen loses 1, so 1 plus. So the oxidation number of oxygen is -2 and the oxidation number of each hydrogen equals to +1. Sample example number 2. We have to find the oxidation state of hydrogen and oxygen in hydrogen peroxide. Now this is the Lewis structure of hydrogen peroxide. H connected to O by single covalent bond. These two oxygen by single covalent bond. This oxygen and hydrogen by single covalent bond. For the heterolytic fission, this bond pair will move towards electronegative, more electronegative oxygen. Also this bond pair will move to the more electronegative oxygen. So ultimately this hydrogen loses its electron, so it will be plus. This it is called peroxide ion. Peroxide ion will have the what? -1 from the left side, another -1 from the right side, and this hydrogen will have the +1. So the oxidation number means per atom. So for the peroxide ion, the charge is what? 2-. So the oxidation number, of each oxygen will be what? Total charge -2 for 2 oxygen. So per oxygen -2/2, so -1. Oxygen number always per atom. So oxygen number of oxygen per atom of oxygen is equal to what? -2/2, because 2 atom will have -2. So per atom -2/2 is equal to -1. So the oxygen number of oxygen in peroxide -1 and hydrogen +1. Now here you see this in this OO bond, since the electronegativity of the two oxygen exactly identical, so heterolytic fission is not possible. We can think about homolytic fission. What is the homolytic fission? Let us see this peroxide ion. So that can be broken by homolytic fission. Homolytic fission means it will have its own electron and it will regain its own electron. So homolytic fission means one electron will go to this side. Half arrow means its own electron will go to this side, its own electron will go to this side. So ultimately there is no extra electron. So O minus remain as O minus, this O minus remain as O minus, because they are not getting any extra electron. So original -1 remain as it is. Similarly original -1 remain as it is. So in this way also we can think oxidation state of each oxygen or oxidation number of each oxygen is equal to -1. Either -2/2 is equal to -1, or you can have homolytic fission. Yes, and ultimately we will have the oxidation state of each oxygen equals to -1. Now sample example number 03. We have to find the oxidation state of phosphorus in orthophosphoric acid. Now this is the structure of orthophosphoric acid. Bond structure, the structural formula of orthophosphoric acid. H3PO4. Now here you see heterolytic fission will happen. Here also heterolytic fission. Heterolytic fission here, 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 here and here. So here for heterolytic fission the electron will move towards oxygen, and here electron also move towards oxygen because oxygen is more electronegative than phosphorus. Here also towards oxygen side, towards oxygen side, towards oxygen side, towards oxygen side, towards oxygen side. Everywhere towards oxygen side. So here this hydrogen will have 1 plus. Similarly this hydrogen 1 plus, this hydrogen 1 plus, because they are losing their electron to the oxygen. So 3 hydrogen and each hydrogen will have 1 plus. Similarly here this oxygen will have from this side 1 electron, from this side another electron, so 2 minus. This also 2 minus, this also 2 minus, this also 2 minus. So 4 oxygen will have 4 oxygen 2 minus. And phosphorus losing 1 electron, second electron, third electron, fourth electron, fifth electron. So phosphorus loses 5 electrons. So phosphorus will have 5 plus. So the oxidation number of phosphorus is equal to +5. Oxidation number of oxygen equals to -2. And oxidation number of each hydrogen equals to +1. Oxidation number of each oxygen is equal to -2. And obviously only one phosphorus atom, its oxygen number is +5. Now you see, to compute the oxidation number, it is not always necessary that we have to draw the Lewis structure or structural formula like that. We have some rules. With the help of these rules, we can also find the oxidation state or oxidation number of an atom in a compound. let us discuss several rules. Rule number 1. The oxidation number or oxidation state of all elements in its any form, allotropic form or any other form, will be always 0. If you have an element, the oxidation number will be always 0. For example, the oxidation number of oxygen in O2 or ozone O3, obviously 0. Also, we can calculate. You see sample example number 4, 5, etc. Again, we will explain. Similarly, oxidation number of sulfur in S2, S3, S6 or S8 will be 0. Rule number 2. Oxidation number or oxidation state of oxygen is normally -2 in its compound, but we have few exceptions. Exception number 1. If we have true peroxide, already explained, you see hydrogen peroxide, the oxygen number of oxygen equals to -1. Example, sodium peroxide, barium peroxide, etc. If we have superoxide like KO2, we can explain. You see the example number 4, sample example 4, again we will explain. The oxygen number of oxygen will be -half. If we have the oxygen difluoride, you see fluorine is more electronegative. Fluorine is the only element which is more electronegative than oxygen. So if we have oxygen difluoride, fluorine will have negative charge because it is more electronegative, and oxygen will have less electronegative, so positive charge. So oxygen number of fluorine actually -1. So for 2 fluorine -2. So for oxygen it will be +2. Again, how to calculate, let us see in the following sample example number 4. Again we will explain there. In this compound, you see oxygen is less electronegative than the fluorine. That's why fluorine will have negative oxidation number and oxygen will have positive oxidation number. Fluorine will have actually -1. So for 2 fluorine -2. Total charge also -2. Since it is a neutral one, oxygen will have also 2 minus. So its oxidation number will be what? Oxygen will have 2 plus. So its oxidation number will be what? +2. Again, fluorine will have the oxidation number -1. So for 2 fluorine -2. So what is the total charge? 2 minus. Oxygen will have 2 plus. So the oxidation number of oxygen in oxygen difluoride will be what? +2. Similarly, if we have alkali metals or alkaline earth metals, so if you have all alkali metals, their oxidation number will be +1, like sodium +1, potassium +1, like that. And if we have alkaline earth metal like calcium, barium, etc., their oxidation number always +2. Now oxidation number of hydrogen in combination is usually +1, but there is only one exception. When the hydrides are formed by the hydrogen with strongly electropositive metal like lithium, sodium, potassium, etc., then it will be -1. Because if you have a sodium hydride like NaH, again we will explain in the following examples. Sodium is +1 charge, so hydrogen will have -1 charge. So obviously oxidation number of hydrogen is -1 and sodium is +1. Now oxidation number or oxidation state of all halogens will be what? Usually -1, but again there are some exception. Exception is what? When they are combined with the elements of higher electronegativity like oxygen, then their oxidation number will be changed. Like you see, if you have a HCl, NaCl, CaCl2, etc., oxidation number of Cl is -1 because it's normal. But if you have the Cl2 here, you see in case of HCl, NaCl, Cl2, chlorine is more electronegative than calcium, sodium, hydrogen. That's why it will have a -1. But in case of Cl2O, oxygen is more electronegative than chlorine. So chlorine will have the what? Oxidation number, positive oxidation number, and oxygen will have the negative oxidation number. We can calculate. If we have Cl2O, the oxidation number of chlorine is what? +1, because actually oxygen will have the total charge 2 minus. So 2 chlorine will have the what? 2 plus, because it is a electrically neutral compound. So per chlorine, so +2 by 2, that is +1. And finally, rule number 6. Now if we have a molecule, then the algebraic sum means sum with sign. The oxidation state of all the elements in a compound will be always equals to 0 because the total charge of the compound is 0. If you have an ion, equal to the charge of the ion. These are the rules. Now sample example number 4. Sample example 04. Arrange the compounds BaO2, barium peroxide, ozone, oxygen difluoride, potassium superoxide in the increasing order of oxidation number of oxygen. So we are going to calculate the oxidation number of oxygen in BaO2, O3, OF2 and KO2. Now oxidation number of oxygen in BaO2, barium peroxide, is -1. How? Let us see. So oxidation number of barium plus 2 into oxidation number of oxygen, because O2, so 2 into oxidation number of oxygen equals to 0, because total charge of the compound is 0. Now barium plus 2, alkaline earth metal we know, plus 2 into oxidation number of oxygen is equal to 0. So oxidation number of oxygen is equal to -2 by 2 -1. That's already we have explained in hydrogen peroxide also. For all peroxides, the oxidation number of oxygen is -1. Now come here, ozone. Oxidation number of oxygen in ozone is 0. Why? Let us see. Formula is O3. So 3 into oxidation number of O is equal to 0, because total charge of O3 is 0. So 3 into oxygen number of oxygen equals to 0. 0 is the total charge of O3. 0, so 0. So oxygen number of oxygen equals to 0. Already we have explained, you see, oxygen number not only O3, N2, H2, all, H2, S2, S6, all will have the 0 oxidation number. Come here, oxidation number of oxygen in oxygen difluoride is +2. Why? Now in OF2, oxidation number of oxygen plus 2 into oxidation number of fluorine equals to 0. Oxidation number of fluorine is what? -1, you know. Actually fluoride, -1. So oxidation number of oxygen plus 2 into -1 for fluoride is equal to 0. So the oxidation number of oxygen equals to +2. So then we can arrange in the increasing order of oxidation number, you see. Next, last oxidation number of oxygen in potassium superoxide, KO2 is equal to -half. Why? Oxygen number of K plus 2 into 2. You see the formula KO2, 2 into oxygen number of O, oxygen, equals to 0. Now potassium +1, because alkali metal, plus 2 into oxygen number of oxygen equals to 0. So oxidation number of oxygen equals to -half. Already explained, you see. So for superoxide, the oxidation number of oxygen equals to -half. Now we can arrange them in the increasing order of the oxidation number, you see. Oxidation number of oxygen for peroxide -1, superoxide -half increases, for ozone 0 increases, and for oxygen difluoride +2. So this is the order, increasing order of oxidation number of oxygen. So accordingly, we have this increasing order. Now sample example number 05. Now we have to find the oxidation state of each of the sulfur atoms in di or pyrosulfurous acid, H2S2O5. Part number B, what is the average oxidation state of sulfur in the same acid? Now you see, if we have the complex species, so we must write down the structural formula to compute the oxidation number or oxidation state of the elements in question or element in question in the structure. So you see how. Part number is the structure of pyrosulfurous acid is this. It is the structure of pyrosulfurous acid. Now to compute the oxidation state of each sulfur, this sulfur and that sulfur, so we must have the heterolytic fission and homolytic fission, where we have the electronegativity different element, heterolytic fission. If we have the same element bonded by single bond or double bond or triple bond, like that, we will have homolytic fission. Like here, sulfur and sulfur, here we will have homolytic fission. But sulfur oxygen, heterolytic fission, sulfur oxygen, heterolytic fission, heterolytic fission, heterolytic fission, heterolytic fission. Similarly, you see, let us see here. So we will have heterolytic and homolytic. Come here. Here you see different oxidation number, oxygen is more electronegative, so heterolytic fission will happen towards right. Similarly, oxygen is more electronegative than sulfur, so heterolytic fission will occur towards left. So oxygen will have 1 electron extra from hydrogen and 1 electron extra from sulfur. So oxygen will have 2- charge. Similarly, this oxygen you see, it will have 2 electrons from sulfur through double bond. Similarly, here also oxygen will have 2 electrons from sulfur because of the heterolytic fission of this double bond. But here heterolytic is not possible because sulfur and sulfur, no electronegativity difference. So it is a homolytic fission. That means this bond is formed due to 1 electron from this sulfur, another electron from this sulfur. In homolytic fission, it will regain its own electron, it will regain its own electron. So no extra charge. So this sulfur will have from this side 1 plus, from this side 2 plus, here no nil, here 2 plus. So this sulfur will have 5 plus. Here I have written, you see, this sulfur will have 5 plus, and this electron remains as radical. And this oxygen will have the what? Minus 2 minus charge, because 1 electron from this hydrogen, 1 electron from the sulfur, so 2 minus. Similarly, it is 2 minus, 2 minus, 2 minus. That's why I have written 3, 2, 3, oxygen 2 minus. This oxygen, this oxygen, this oxygen. Hydrogen plus. Come to this sulfur. Now, because of this homolytic fission, it will have one, it will retain its own electron, Now, here, heterolytic fission, losing 2 electrons, so 2 plus, 1 electron, so another plus, so 3 plus, 3 plus. So sulfur will have 3 plus, and 1 electron, it will retain its own electron because of homolytic fission from this side, left side. Similarly, this oxygen, 1 minus, 1 minus, 2 minus, this oxygen 2 minus, so 2 oxygen 2 minus, H plus. So ultimately, what is the oxygen state? Charge 1 plus, so plus 1 oxygen state. Each oxygen number always each oxygen atom. So each oxygen atom will 2 minus, so each oxygen atom will have the oxygen number minus 2. Sulfur plus 5 plus charge, so oxygen number plus 5. This sulfur 3 plus charge, so oxygen number plus 3, oxygen minus 2, hydrogen plus 1. Therefore, you see the oxidation number of sulfur, separate oxygen number is required. So the oxygen number of sulfur joined to 3 oxygen, 1, 2, 3, will be plus 5, this one, plus 5. And the oxygen number of sulfur joined to 2 oxygen, this will be what? Plus 3, answer. Now, we have the interest on average oxygen state also. So how to find average oxygen number means obviously only one value, unique value. So you see how to calculate. There are 2 methods. Yes, I will show you. So let the average oxidation state of sulfur be X. This sulfur be X. Then the structure of the acid. Oxidation states are written in bracket. So this is the structure. Already we have explained. It will have the plus one oxygen number. This oxygen will have the minus 2. This oxygen will have oxygen number minus 2. Average oxygen number of sulfur is X, so it is also X, equal. Average value means equal oxygen number. So it will also have the X value, Oxygen minus 2 plus 1. So this yields what? Total algebraic sum of the what? Oxygen number of all elements must be equals to 0, because the acid is what? Neutral, but acid is, total charge of acid is 0, that's why algebraic sum of the oxygen numbers of all the elements must be equals to 0. Yes, you see, oxygen number will be equals to 0. So for 2 sulfur 2x, for 5 oxygen 5 into minus 2, for 2 hydrogen 2 into plus 1 is equal to 0. So 2x equals to plus 8. So average oxygen state of each sulfur is plus 4. We can have another concept also. Already individual oxygen state we have already obtained, plus 5 and plus 3. So plus 5 for the left sulfur and plus 3 for the right sulfur, divided by 2. So also same answer we can have plus 4. Now sample example 06. Now we are going to find the oxidation number of sulfur in Marshall acids. Marshall acid is peroxodisulfuric acid, H2S2O8, and it is the structure. Now here you see, this sulfur and this sulfur will have the same oxidation state because it is a symmetrical structure, you see. OH, double bond, double bond, double bond. Exactly, it is a plane of symmetry. So it is a symmetrical structure, so both the sulfur will have same oxidation number. That's why we have chosen X and X. Rest we know, same heterolytic fission. So plus 1, minus 2, minus 2, minus, but it is a peroxo linkage, be careful. So minus 1, minus 1. Minus 1, minus 1. Because please you see here, from here heterolytic fission 1 minus, from here heterolytic fission 1 minus. So total 2 minus for 2 atoms. For 1 atom, minus 2 by 2 is equal to minus 1. Be careful, already explained. So minus 1, because it is a peroxo linkage. This is the oxygen coming from peroxo linkage. It is oxide, oxo. They are called oxo linkage, minus 2 this. So we can calculate, you see, 2 into oxygen number of sulfur plus 1 and 2, 2 into oxidation number of hydrogen plus how many oxygen, 1, 2, 3, how many oxide, oxygen from oxo linkage, 1, 2, 3, 4, 5, 6. So 6 into oxidation number of oxo, the oxo means -2, and 1 and 2, 2 into oxidation number of peroxo linkage is equal to 0. Now 2 into sulfur X, so X I have written, plus 2 into hydrogen plus 1, plus 6 into oxo means -2, so -2, plus 2 into peroxo -1, 2 into -1 is equal to 0, implies X equals to plus 6. So the oxidation number of sulfur is equal to plus 6. Sample example 07. Now we have to find the oxidation number of iron in Fe 0.94 oxygen. Now clearly you see 0.94 into oxidation number of iron plus oxidation number of oxygen equals to 0. Total charge is 0, so 0. So 0.94 into oxidation number of iron plus oxygen is oxide, so -2 equals to 0. So oxidation number of iron equals to 2 by this equals to 100 by 47 answer. Now sample example 08. Now you see, now when the molecular formula is given, then if we have a molecular formula, then average oxidation number is required. But when the structural formula is given, we need distinct oxidation number of element. Yes. So you see here, we have to identify the oxidation number of sulfur in tetrathionate S4O62 minus. The molecular formula, the S4O62 minus tetrathionate ion. So we have to identify the oxidation number of sulfur in tetrathionate ion, having the molecular formula given and the structural formula given. In molecular formula we will have average value. In the structural formula we will have distinct values. Now solution. Now, so here you see, since the molecular formula is given, part number A, we need the average oxidation number of sulfur. So let the average oxidation number of sulfur is X. Then here also we need structure. It will help us to compute the average oxidation number of sulfurs. So then from the structure of S4O6, yes, it is the structure of S4O6 2 minus that I have drawn. We have the 4 into oxidation number of, there are 4, 1, 2, 3, 4, 4 into oxidation number of sulfur plus 6 into 1, 2, 3, 4, 5, 6. 6 into oxidation number of oxygen equals to total charge 2 minus, so oxygen number -2 of the radical. So 4x plus 6 into -2, all are oxide group. So -2, -2, -2, -2, -2, -2. So 6 into -2 equal to -2. So 4x equals to plus 10. So x equals to plus 5 by 2 answer. But here you see the structural formula, part number B, we have to find the distinct oxygen number of this sulfur, this sulfur, this sulfur and this sulfur, because the structural formula is given. Now you see, here you see heterolytic fission towards oxygen, heterolytic fission towards oxygen. Here also, but here homolytic fission. So this sulfur will regain its own electron and this will retain its own electron. Similarly here also, here no breaking. So here also you see homolytic fission, because it is also sulfur, it is also sulfur. So this will have one electron, this will regain its own electron and this sulfur will regain its own electron. So we will have what? 1, 2, 3, 3 O2 minus, O2 minus, O2 minus, O2 minus, 3 O2 minus. And for this sulfur, 1, 2, 3, 4, 1, 2, 3, 4, 5. 5 plus, because this sulfur loses 5 electron. 2 electron along this double bond, for this double bond, 1 electron for the single bond and the 2 electron for the double bond. And here you see no change, because it will regain its own electron, it will retain its own electron. So sulfur will have plus 5 plus this electron it regains. Now in this case, sulfur and sulfur, so it will also regain its own electron, it will also regain its own electron by homolytic fission. And again this sulfur same as before, 1, 2, 3, 4, 5 plus 5 and this oxygen -2. So ultimately we will have 1, 2, 3, 3 O2 minus. This sulfur will have plus 5. One electron, yes, it regains its own electron, this electron. This sulfur SS bond, one electron coming from this, one electron coming from it, it will regain its own electron, it will also regain its own electron. This sulfur is also plus 5, and this oxygen 1, 2, 3, 3, oxygen 2 minus. So its oxygen number minus 2, it is a plus 5, it will be 0. Let us see how to calculate. It will be plus 5, it will be minus 2. What is 0? 2 into oxygen number of sulfur. 2 sulfur, so 2 into oxygen number of sulfur equals to 0. Total charge is 0, so 0. So oxygen number of sulfur equals to 0, so it is also 0. So thus the oxygen number of each sulfur bonded to oxygen, this one and this one, is equal to plus 5, which is plus 5 and plus 5. And the oxygen number of each sulfur associated with single bond, these two sulfur associated with single bond, single, you will what? 0. Also we can find, from here we can also find the average oxidation number of sulfur also. Here you see plus 5 for this sulfur, 0 plus 0 for these two sulfur, and plus 5 for this sulfur. Total sulfur atom 1, 2, 3, 4, so divide by 4. Also we can have 5 by 2 average oxidation number of sulfur. Now suppose number 09, we are going to find the oxidation state of chromium in CrO5. It is the correct formula of CrO5 is this, because this is a 2 peroxo linkage, it is oxo linkage. It has butterfly structure like that. Chromium double bond O, and O2 means O2, O2, O2. So it is actually a peroxo compound. For this peroxo, minus 1, minus 1, minus 1, minus 1, it is the oxo minus 2. So we can find the oxygen number of chromium. How? Oxygen number of chromium plus 4 into 1, 2, 3, 4 into peroxo oxygen plus oxygen state of only one, oxygen of oxo oxygen is equal to 0. So oxygen state of chromium plus 4 into peroxo means minus 1, and oxygen state of oxo is minus 2 is equal to 0. So oxygen state of chromium is what? Plus 6. Now sample example number 10. It is an organic compound. So let us see how to find the oxidation number of carbon etc. from organic compounds. Sample example number 10. We have to find the oxidation number of C1, carbon 1, C2, C3 in propene. Now first we will find the oxidation number of distinct oxidation number C1, C2 and C3, and then we will find the average oxidation number of carbon in propene. Now to find the distinct oxidation number, we must write the structural formula. It is the structure of propene. You see it is CC bond, so here no electronegativity difference, so homolytic fission. CC bond also homolytic fission, So what will happen? All this carbon will retain their own electron. So this carbon will retain its own electron. This also this. It will have 2 electron own. It will also have 2 electron its own electron. So no extra charge. The homolytic fission, only they retain their own electron. So no extra charge. Now it is a carbon number 1. So for C1, oxidation number of C1 plus 2 into oxidation number of hydrogen equals to 0. Total charge 0, 0. So oxidation number of C1 plus 2 into hydrogen plus 1 is equal to 0. So oxidation number of C1 is equal to minus 2. Similarly, oxidation number of C2, second carbon C2. So oxidation number of C2 plus oxidation number of hydrogen also equals to 0. So oxidation number of C2 is equal plus hydrogen plus 1 is equal to 0. So oxidation number of C2 minus 1. Similarly for C3 carbon, oxidation number of C3 plus 3 into oxidation number of hydrogen is equal to 0. So oxidation number of C3 plus 3 into plus 1, 0, so minus 3. Now part number B, average. For average oxidation number we need the what? Molecular formula C3H6. So let the oxidation number of carbon is suppose X. So 3 into X plus 6 into plus 1 is equal to 0. So X equals to minus 2. Also from distinct oxidation number also we can find the average oxidation number. How? Oxidation number of C1 plus C2 plus C3 divided by 3. So you see minus 2 minus 1 minus 3 divided by 3. So minus 6 by 3 minus 2. Same answer we have. Similarly, AC11, another organic compound, we are going to find the oxidation state of carboxylic carbon. This is a carboxylic group. We are going to find the oxidation number of this carbon. And part number B, compute the average oxidation state of carbon in the carboxylic acid, that is acetic acid. Now to find the oxidation number of the carboxylic carbon, that is distinct oxidation number, we need the structural formula. It is the structural formula of acetic acid, this acid, CH3C double bond of this. So here homolytic fission will happen because CC bond, no electronegativity difference, same atom, always homolytic fission. So we will have CH3 radical plus carboxylic acid radical. Now let the oxidation state of carboxylic C is X. So X, there are two oxygen, it is same as before, you see, -2 plus 1. So 2 into -2 plus for hydrogen 1 into plus 1 equals to 0. So X equals to plus 3, oxygen number of this carbon. And if we have the average, so the average oxygen number, so only we need the what? Only molecular formula. So H4C2O2 molecular formula. So 4 into oxidation state of hydrogen plus 2 into oxidation state of carbon, average value, plus 2 into oxidation state of oxygen equals to 0. So 4 into hydrogen plus 1, that is required. 2 into average oxidation state of carbon plus 2 into oxygen minus 2 equals to 0. So oxidation state of carbon equals to 0. Next, as say, we are going to find the oxidation number of elements connected by coordinate bonds. Now you see, so if M is the less electronegative atom and X is the more electronegative atom, then coordinate bond means the two electron, this bond pair is coming from only M. So since M is less electronegative and X is more electronegative, so heterolytic fission will happen in this direction towards X. So M loses 2 electron, so oxygen number will be plus 2 because it will have the charge 2 plus, and X will have the charge 2 minus, so its oxidation state will be what? Minus 2. Clearly explained here, you see. For Mx, it is a heterolytic fission. M loses 2 electrons, so it will have 2 plus. X gains 2 electrons extra, so 2 minus. So its oxidation number is plus 2, its oxidation number of X is minus 2. But if you have this type of coordinate covalent bond, and it is unfavorable, from more electronegative to less not possible. A less electronegative can donate electron pair to the more electronegative atom. In this case, more cannot donate electron pair to the less, so it is unfavorable. So in this case, all will have the 0 oxidation number because this type of bond cannot contribute the oxidation number of M and X. Sample example. We are going to find the oxidation number of nitric acid, HNO3. It is structural formula. First method. You see, oxidation number of nitrogen. This nitrogen equals to what? Because of this NO bond, there is a what? Heterolytic fission towards oxygen, so it will have plus 1. So plus 1 because of heterolytic fission of ON bond plus double bond, N double bond O. The heterolytic fission, so it will have plus 2 because nitrogen loses 2 electron. It is a covalent bond, favorable covalent bond because less electronegative to more electronegative, favorable bond. So because of this heterolytic fission, the nitrogen will have plus 2 because nitrogen loses 2 electrons, so plus 2. Yes, so total plus 5, plus 1, plus 2, plus 2, plus 5. Second method, you see, we can also write normally oxidation number of hydrogen plus 3 into oxidation number of oxygen, 1, 2, 3, plus oxidation number of nitrogen equals to 0. Now, hydrogen plus 1, oxygen you see all minus 2 already explained in the first method. So 3 into minus 2 plus oxidation number of nitrogen equals to 0, so plus 5 oxidation number of nitrogen. Now sample example 13, hydrogen cyanide, HNC, double bond and one is coordinate bond, so that octet is satisfied here and here. First method, you see, oxidation number of nitrogen Yes, you see -2 for N double bond C -2, N double bond C. For this heterolytic fission, nitrogen is more electronegative. So heterolytic fission will happen towards nitrogen. So nitrogen will have the what? 1 electron extra, another electron extra, 2 minus, so -2. And then this hydrogen -1, because in this heterolytic fission the hydrogen will donate 1 electron to nitrogen, so nitrogen will have 1 minus charge, so -1. And it is a unfavorable coordinate bond, you see, because more electronegative to less electron not possible, unfavorable, so contribution 0. So for NC it is 0, so total -3. Second method, you see, we can say oxidation number of nitrogen plus oxidation number of hydrogen plus oxidation number of carbon equals to 0. Oxidation of nitrogen, hydrogen plus 1, and oxidation number of carbon already calculated plus 2, because only this will have only these two double bond will undergo heterolytic fission, that is carbon losing only 2 electrons, so plus 2 is equal to 0, and implies oxidation number of nitrogen equals to what? -3, because plus 2 plus 1 plus 3, so -3. You see hydrogen plus 1, nitrogen -3, carbon plus 2.